Hello. Let us quickly finish the section of last time about undecidability. So last time we showed that the halting problem is undecidable, and what we are left with is to show how we can use this to show that other problems are undecidable. So the technique we will use now that we have one undecidable problem, we can call it the reduction technique. And the setup is like this. So our goal is to show that some m is undecidable. And the approach we take is as follows. So let H denote the halting problem. We will construct a function that reduces the halting problem to m. Yeah. So we construct a total computable function phi such that some element is in the halting problem if and only if phi of x is in M. And now it follows that if M was decidable, we could just use phi to translate any kind of element we're interested in, if it belongs to the halting problem, into an element of M, and then use the procedure that decides M to tell us whether this element was in H or not. So yeah, then it follows that if M was decidable, H would be 2. This is somehow completely the same as showing that a problem is NP-complete. Just reduce another NP-complete problem to it. So let's show this on an example. So definition, let T1 and T2 be Turing machines we say that they are equivalent if they implement the same computable function. If phi T1 is the same as phi T2, and we write T1 is somehow equivalent to T2. So now we are ready to prove this proposition. Let D be the set of all tuples of descriptions of Turing machines which are equivalent. Is undecidable. So it should be a pretty straightforward process. So suppose for contradiction that D is decidable and that it's decided by some Turing machine D. So decided by, I just mean the characteristic function of this set is implemented by a Turing machine. So suppose for contradiction that there exists a Turing machine D which decides D. And now we will essentially define a Turing machine which implements this translation function. So we define a Turing machine T as follows on input X. Or should we call it N? It really doesn't matter. So first we're gonna compute the description of T, compute T, where, okay. T prime, whatever, where T prime has the Gödel number n, and essentially we're now trying to use D to answer the question whether phi n is defined. This is what we're trying to do. So we somehow have to construct two clever Turing machines to ask whether they're equivalent or not. So compute the description of T prime n, where phi of T n prime m is 0 for all m different from n, and phi T prime n at n is 1. So now we're kind of, if T n prime n halts and is undefined otherwise. So since we care about this value, let's just define this function to be 0 everywhere else. And now we just, if this Turing machine halts, we don't care what is its output, we just output 1. And otherwise, so that this is really a computable process, we have to be undefined otherwise. So hopefully you believe that we can define the Turing machine T prime n like this. And we compute its description. And we will compare this against yet another Turing machine, which we can call delta n, where delta n is a Tm which halts with output 0 for all inputs m different from n, and halts with output 1 for input n. So from n, we retrieved the Turing machine that has the Gödel number n. We modified it into another one where we only care about what it does on the nth input. And we have created yet another Turing machine, which just detects whether the input is n or not. And now we just output, or like, we simulate d on input t prime n delta n and output that. Good. So now the claim, it should be pretty straightforward, is that this Turing machine T decides the halting problem so let n be such that phi n on n is defined, aka n is in H. Then what happens? Then delta of t prime n delta n is 1. It's because, n is defined, which means that dn on input n is 1. So this means that dn prime is equivalent to delta n. So the Turing machine D will output 1. And what if phi n of n is not defined? Then the Turing machine T prime on the input n diverges, which means that T prime n on input n also diverges, which means that Tn prime is not equivalent to delta n because this function is total. So d of Tn prime and delta n is 0. Great. So that's the contradiction with our assumption that D is decidable. Are there any questions for this? You will have a chance to practice this in the exercises.
I don't understand the point of the first point of that. Point number 1, where we compute T prime with the number n, and then we compute another T prime n.
So what is our goal? Well, our goal is to figure out whether n is in H. So we are interested whether phi n on n is defined. So what we can first do is find some Turing machine that implements phi n. That's exactly the Turing machine T prime, which has Gödel number n. So this is the first thing we do. We know this is computable because the Gödel numbering is totally computable. And now we would like to compare this against something such that the result is a 1 if and only if T prime on n halts, n is a 0 otherwise, right? So we want to compare this whole Turing machine on every, like defined for every input against something, but you only care about its nth input. So that's why we're kind of stripping T prime down, where we essentially say, if the input is anything else than n, we just set it to 0, so that we can compare it against a function that is also 0 everywhere except for the input n. And we then just essentially, when comparing these two Turing machines, they will be equivalent if and only if they are the same on the nth input. That's the thing, yeah.
So T prime. So shouldn't be.
Or is there some mistake?
I don't know.
Yes?
Yeah, I think in step 2, phi t prime and of n should be defined if t prime holds.
Oh yeah, we're already doing some recursive definitions. We will only be able to do that after the second lecture today. Great, thank you. So, no.
The n was right, I think.
Yeah,
The other one on the right.
Yeah.
Oh yeah, oh yeah, oh yeah. Yes, we're defining Tn prime via T prime. Wonderful. Thank you. So this kind of concludes the standard introduction, a very brief one, to the theory of computation. And now we will finally be able to talk about self-referencing programs and self-replication. So the next topic is Quines. Scene. Beamer. Oh la la. Okay. Right. And suppose that we would like to design a blueprint such that as the processor is reading it, it's gonna create an exact same copy of the blueprint and puts it on the tape of the new machine, right? So we have kind of stripped down all the physical aspects of self-replication, and we're just kind of wondering, can we come up with such a blueprint that will be able to create its own description such that the machine can copy it on the new machine's empty tape? And, well, luckily for us, we can formulate this question quite precisely in the language of Turing machines. So the question is there a Turing machine Q which from an empty input outputs exactly its own description. So can we design such a queue? So hopefully, let's see how this relates to our problem of creating a self-referencing blueprint. So let U be the universal partial computable function or maybe we can see it now for our purposes as a function which operates on sequences. So what happens if we plug in to U the description of Q and an empty input? Well, the output is exactly Q. So if we kind of interpret U as the functionality of this processor that is reading whatever it gets on its tape, then we see that this universal partial function will interpret or will kind of simulate Q on the empty input and recreate itself somewhere on the new tape, right? So we can kind of see it as some sort of a self-replication process. Maybe we can modify U to be such a partial function that instead of simulating Q on input N, it kind of does not erase this description, so it kind of outputs whatever it got here concatenated with the output of Q on N. So for this new modified universal partial computable function, if we plug in the Quine and an empty input, we get exactly 2 copies of Q. So okay, we have some self-referencing program that, if it's plugged into the right universal computable function, can somehow self-replicate itself. So what does this mean in the modern programming language? So in the language of modern, of modern programming, we can interpret the question as this. Can we write a program which outputs exactly its own source code? So such a program is typically called a Quine. We will write it with a small q, but it's named after a logician whose name was Quine, who was also working on topics of self-reference. So maybe now is a good time to pause and think how we would write such a program, for instance, in Python. That's going to be the language of my choice. But before we do that, let's make this truly challenging and distinguish true deep quines that come from some universal recipes and ones that don't feel so universal. The thing is, if you're too good with Python, you might be familiar with some very fancy functions that, for instance, can kind of fetch the source code of a program, or like, this is not what we want, and it's hard to formalize this precisely. So I'm just going to show you 3 examples of quines that don't feel as universal as they could be. So the first one is the syntax you see here. Can you see it well? So this is not even like a syntactically valid code, but it's written in such a way, and it's stored in a file called isitaquine.py, such that if we run this, we get an error message which happens to perfectly match with the one we wrote. So this program does output its own source code, but does it? And then let's get into more subtle issues of universality. Maybe when I talk to programmers about this, they usually suggest a solution which looks like this. So this is a program stored in a file called Quine in memory. Let me just double check the camera is. And what it does is somehow just opens the file, reads the contents of it, and prints it. So like if we run this code, we do get exactly the same. But what is the issue here? The issue is that as your program gets compiled and executed, essentially the interpreter or the operation system or whatever is executing it has access to additional inputs, for instance, to your file system, so it can actually fetch the source code. If we were to implement this by a Turing machine, we would have to introduce some extra tape where the actual string of the code is written, which would act as this additional input. So what you could do is somehow mingle with your system to, let's say, prohibit your interpreter or your operation system to have, or I guess the interpreter to have access to the file system. And still, if you write Python code, it would be a computationally universal language, like you could implement any computable function you would want, but this type of Quine would stop working. And this is essentially the same problem with this following code, which just kind of hides this calling or fetching the source code from the memory by this function inspect. So again, if we run this, we do get exactly the same. So these Quines are interesting, but I'm saying we can do better. We can really construct a Quine that will work in any programming language that is rich enough, no matter what are the particularities in how it works. So let's try to write our first honest, but naive, but honest attempt. So I don't know, we can define some data, which we don't know what it is yet, and then we would probably want to print the data. So this is not great. So maybe we can modify this to get to actually print the whole first line. So let's now ignore quotes. Quotes are a story for themselves. But now we don't have the second line, so what can we do? We can kind of maybe try to replace the question marks with something smart, for instance, what we have. But still, we're somehow only getting the first line. I mean, we can also just print the second line. Oh. So now we have the first two lines, but we don't have the third line. And as you can see, in this naive way, we will always try to catch up with the previous version of your code by building a new code. And the question is, can we ever really catch up? Can we find a fixed point of this process that will not result in an infinite code that we're trying to write? And the answer is yes, we can do that. And we will essentially give such a recipe in the language of Turing machines right now. So that's it for demonstrating that I am not a good programmer. So beamer off. And we have to switch the recording. Okay, this should work. And the camera should be here. So, existence of a Quine. So just one technical remark that it will be very useful for the rest of today is something about composing Turing machines. So, remark. Suppose we have Turing machines A and B, for instance, with the same input alphabet. And the claim is that there, or like we fix a canonical way of modifying the concatenation of these two descriptions into the description of another Turing machine T, where T implements the function which essentially first runs A and then runs B. Right, so if these two functions are partial computable, their composition also is. And there is infinitely many Turing machines that implement this composition. So we just want to pick one that will be, let's say, the canonical representation so that we can refer to it as the Turing machine that implements it. And there's multiple ways you can do it. All that matters is that this transformation is like total computable. So in a bit of a hand-wavy way, we have our description of A. And then we have our description of B. So this is why it was nice to put the extra parentheses around so we know where one description ends and another starts. But these are just details. And what we have here is the encoding of, let's say, the initial state of A, some symbol S, and then the outcome being some other state of A, some other symbol, and the encoding of the movement of the head, da-da-da. And lastly, we will have some, I don't know, encoding of another state of A, some other symbol, and then let's say that this instruction will go to the halting state of A and something else. So this is kind of some description of A. And B then starts with what happens if we have the initial state of B and we are in some state T. And we're reading some type symbol T. So we will move to some other state and so on. So the process works as follows. Let's say we can say re-encode all states of B. So they don't collide with any representation of a state with A, so we can just distinguish them apart. So that Q, I, A are distinct from Q, J, B. And secondly, all we have to do is instead, so what does this Turing machine do? On input X, it first kind of runs A, and if A halts with some output Y, then it runs B with that output Y. So essentially, whenever A had an instruction that it should halt, we just have to rewire this instruction into the initial state of Q of B, of Q0B. And this way we ensure, so we map essentially Q halt A into Q0B, and then we remove the extra parentheses. So we remove these two, right? So we will refer to T as a Turing machine that we will denote like this, just the composition of A and B. And in the time that we have, I don't know where to write. So let us prove that there exists a quine in the sense of the Turing machine that outputs its own description. So we will decompose Q into two Turing machines, A and B. And somehow we will make A such that it constructs the description of B and B such that it constructs the description of A, but in a way that there is no cyclic dependency in the definition of the two. This is how we will solve the self-reference problem, such that they recreate each other's description while avoiding a cyclic dependency. And in some sense, A will play the role of data, and B will play the role of a Turing machine that acts on this data. I just want you to remember this when we discuss physical self-replication. So let's start by, and then we will put Q equal to AB. So let PC denote a Turing machine that will always just print C. This is the role of the data, let's say. Be a TM that always halts with output C. We define B first. So let's not put B in the definition so it doesn't feel cyclic. So check if X is a valid representation of, is a valid description of a Turing machine. And if not, just halt. We don't really care what happens in this scenario. Otherwise, compute the description of the Turing machine that prints X. So essentially compute Px. It's pretty straightforward. And lastly, output a Turing machine that first does Px and then does T. So this follows exactly the logic we just talked about. So at this point, B has access to the description of Px and to the description of T. So all it has to do is modify them to get the description of our canonical choice of the Turing machine that first runs Px and then runs T. So can you guess how we will define A? So we put A to be a program that just prints the description of B. So now let's check that everything is okay. essentially, as we define B, there is no dependency on A. This is just a well-defined Turing machine. And now we define A such that it depends on B, and that's fine. So what happens if we put Q to be the composition of A and B? What happens on empty input? So first we run A. So A outputs B, right? Then B is executed on input, which is its own description, and outputs PB composed with B, and PB is A, and AB is Q. So indeed, from an empty input, Q outputs its own description. In the lecture notes, you see an idea of how you can implement A and B in Python. And I encourage you to do a little optional exercise where you just modify these two to really get a Quine. And as you can see, somehow this procedure should work no matter what programming language you choose, as long as it's strong enough to check whether something is a valid source code, define functions that print that source code, and compose functions. We have not used any extra sugar. So maybe we can end this particular section with an informal definition, which I will write in blue so that you don't take it too seriously. But I need space. So this is, let's say, an attempt to distinguish this type of a Quine construction from the ones we have seen before, which were exploiting some particular property of the underlying universal system that executes such a code. So So what could we mean by a universal Quine recipe? Is a Turing machine R which, whenever it gets on its input some U, a description of a universal Turing machine it outputs the description of a Quine with respect to the Turing machine such that if we execute this universal Turing machine, if we execute this program with respect to this universal Turing machine, on an empty input, this program will be self-referential and produce an exact copy of itself. So we would like this R to be universal in such a sense that it does not exploit anything particular about U. And we can hopefully persuade ourselves that such a construction is exactly a universal recipe of how to obtain quines. So hopefully you can now see the difference, and whenever you see a quine, you can ponder the question whether it comes from a universal recipe or not. And that's it. Let's take a break.